Hello and welcome to this lecture. So now in this lecture we're going to start looking at the actual diagonal matrix that corresponds to a linear transformation which is diagonalizable. Okay, so we've seen how if you have a operator which is diagonalizable, you can find a basis of eigenvectors, and then with respect to that basis, if you find the matrix for that linear operator, you will get a diagonal matrix. Okay, so I want to show you how that works and show you these diagonal matrices and explicitly show some of these, the similarity transform that we saw, S, A, S inverse, and how that comes about, and all of that from multiple angles, so that the ideas become firmer. Okay, so let's get started. Okay, so we'll once again start with our very simple examples. I'll repeat many of the examples we've been seeing this week so that it's comfortable for you. So let's begin with this matrix A, this lower triangular matrix, and this we are thinking of as representing an operator T from R3 to R3, and you're going to use canonical basis. When I don't mention the basis, it's canonical basis. So what does that mean? The basis vector E1, which is 1, 0, 0, if you send it through T, you're going to get 1, 1, 1, which is the first column, right? T of E1. Second column is T of E2, and then E2 is 0, 1, 0. Through T, if you go, you get 0, 2, 1. Then E3 is 0, 0, 1, and through T, if you go, you get 0, 0, 3. Okay, so these output vectors, they are also in the canonical basis. They are expressed in the canonical basis. Okay, so the input vectors are the canonical basis, output vectors canonical basis, and you get the columns here of A representing the T. Okay, so this is the picture. This is a very familiar picture that you know. Okay, so now I know I have eigenvectors here, and I have three linearly independent eigenvectors. I'm going to name them. The first one I'm going to call V1, second one is V2, the third one is V3. The corresponding eigenvalues are 1, 2, and 3. So these are the eigenvalues. Okay, this 1, 2, 3 are eigenvalues. The vectors here are eigenvectors. So you see three independent eigenvectors, basis for R3. Okay. So now what does it mean for these things to be eigenvectors? Let's go and see that once again. It means that if V1 goes through T, it gets transformed through T, you get V1 again, right? The eigenvalue is 1. So V1, T of V1 is 1 times V1. So you get V1 again. Now V1 is what? 1 minus 1, 0. And remember, this 1 minus 1, 0 is again in the canonical basis. Okay, so expressing the output vectors also on the canonical basis. V1 itself is expressed in canonical basis. Okay, so keep that in mind. Now what happens to V2? V2 goes to 2V2, which is 0, 2, minus 2. Again, this is expressed in the canonical basis. Remember, this is V1, this is 2V2. And finally, V3, go through T, if you go, you get 3V3. That's the eigenvector definition. So you get 0, 0, 3. These are in the canonical basis. Okay, so all up to here, there's no issue. So now we're going to try and change the basis. So when I change the basis, what should I do? I should now start expressing the output and the input vectors in the basis that I want. What is the basis that I want? I want the basis V1, V2, V3, right? So this is the eigenvector basis. So I'm going to express that in this basis. So what is the meaning of expressing this V1 in the basis V1, V2, V3? Remember, V1, V2, V3 are linearly independent. So V1 in the basis V1, V2, V3 is simply 1, 0, 0. 2V2 in the basis V1, V2, V3 is 0, 2, 0. 3V3 in the basis is just 0, 0, 3, right? So it remains the same. So I'm going to switch that. Okay, so I hope you see that. So I've not changed anything else except these three output vectors alone, I've expressed in the basis V1, V2, V3 and not in the canonical basis. So hopefully you see that in the canonical basis, these are these guys. In the basis V1, V2, V3, V1 is simply 1, 0, 0, 2V2 is just 0, 2, 0, 3V3 is 0, 0, 3. Okay, I hope you see this. Okay, so it's very, very simple. So that's the thing. So now how do I find the matrix of T with respect to this basis V1, V2, V3? Remember, in the basis V1, V2, V3, I have my basis vector V1 going to 1, 0, 0. V2 goes to 0, 2, 0. V3 goes to 0, 3, 0, 3. These are my basis vectors, right? These are my vectors in V1, V2, V3. What is the coordinates of V1? 0, 1, 0, 0. V2 is 0, 1, 0, 1, 0. V3 is 0, 0, 1. So, it's very similar picture to this I have. So, if this resulted in a matrix like this V1, V2, V3 going to V1, 2V2, 3V3 is going to result in a matrix that looks like this. So, I hope you see this. The matrix of T in the basis V1, V2, V3. The first column is T of V1, which is actually V1 itself. It's expressed in the basis vector V1, V2, V3, so you get 1, 0, 0. Second column is T of V2, which is 0, 2, 0 in the basis V1, V2, V3. Third column is T of V3, that's 0, 0, 3. And lo and behold, it's diagonal. So it is going to be diagonal when you use the eigenvector basis. Okay. So make sure you understand this, this sequence very carefully, how we argued it out. and then how this diagonal matrix resulted. Okay. So now I'm going to show you one more way in which you can think about it, which is the similarity transform, right? So I'm going to do that similarity transform in some gory detail just to show you how that comes about, purely thinking of it in terms of matrices. Okay, so you can think of it in terms of change of basis, multiplying by S inverse S and all that. So that's possible. That's the way in which we described it when we looked at it theoretically. Now I'm going to give you a purely matrix type interpretation. Sometimes that is also useful to have. Okay. So we'll begin with this very simple result. Okay, see, for 1, 2, 3 matrix, okay, so this A matrix 1, 2, 3 on the diagonal, 1, 1, 1, 1 minus 1, 0 is an eigenvector, right? So which means what? When you multiply with 1 minus 1, 0, I'm going to get 1 minus 1, 0. So this is what is going on with this matrix. Okay. So is this clear? I hope you see this. So when you multiply by 1 minus 1, 0, the first column, right? So what does it do? So this 1 multiplies the first column, minus 1 multiplies the second column, 0 multiplies the third column, and you get the first column out, right? The output column is basically the linear combination of the columns here with 1, minus 1 and 0. So you get this. Okay. So I hope you see this is very simple. Okay. Now I'm going to add the second vector, 0, 1, minus 1, right? So 0, 1, minus 1, I'm going to add to this equation. So how do I add it? I'm going to add it as another column here. Okay. So the same matrix A that I have here, I multiplied with only one vector now. So I'm going to multiply with a matrix here with two columns. The first column is the same as before, 1, minus 1, 0. The second column, I'm going to make it 0, 1, minus 1. Okay. What is the 0, 1, minus 1? Is the second eigenvector. Now remember, I can do column by column, column wise multiplication, right? So the first column multiplied this guy and gave me this output here, this column, right? Now the second column will again multiply the same way, multiply A the same fashion, and you'll get the second column here, right? So column by column, if you do the product, it's the same as multiplying the vector one at a time, right? It's just kept together, right? Isn't it? So the second vector, because it's an eigenvector, it will multiply A and it will give you 2v2, which is 0, 2, minus 2. Okay. So this is just matrix multiplication because I'm using eigenvector here. So I got the 0, 2, minus 2 here. Okay. So this is just column wise multiplication. Now here comes a little bit of a trickery. So this matrix I can write as follows. Okay. What did I do here? I simply retained the first column as it is. The second column, instead of 2v2, I kept only v2. Okay. So only 0, 1, minus 1. And then what did I do? I put up a diagonal matrix on the right. Okay. I put up a diagonal matrix on the right. So with 1 and 2 on the diagonals. So now what happens? These two are exactly the same. I hope you're convinced that the right hand side of these two are exactly the same. Again, think of the column wise multiplication. You multiply column wise with this matrix. The first column will multiply the two columns here correspondingly. So 1 into this plus 0 into this. So you get this guy. Likewise, the second column is 0, 2 is going to multiply this guy and you will get 0, 2, minus 2. I hope you see the column wise multiplication. So this column wise multiplication idea with the matrix is sort of central to the linear transformation view, and no wonder that plays a big role in this similarity transform also. So now we have added the two eigenvectors here, first and second one in the first third column. What am I going to do? I am going to add a third column, which is the third eigenvector, and do the same sort of multiplication. So now you can easily see what will happen. When I add the third column 0, 0, 1, I will add another column here at the output, which will be 0, 0, 3. Right? It just picks out the third column, isn't it? Easy enough to see. So now I'm going to do the same trick that I did here. Okay. So I don't want 0, 0, 3, I want 0, 0, 1. Okay, I don't want 0, 2, minus 2, I want 0, 1, minus 1, because I want the v1, v2, v3 to be in the columns here. Okay. So if I do that, I have to multiply with the diagonal matrix on the right. Okay. So I do that here. Okay. So you see the last column, I made it 0, 0, 1, and I added a diagonal matrix here with the third entry 3. So now you see this is just an identity. And wonderfully well, these two matrices are the same. This matrix and this matrix are exactly the same, right? So I put v1, v2, v3, and I adjusted the right hand side with this diagonal to make v1, v2, v3 again. So now I have this matrix is the original matrix A. This is my S matrix. I'm going to call this S. Each column is the eigenvector that I had here, and the same S appears here, and then you have a diagonal guy here. Okay. So this is actually very similar to the change of basis sort of thing, except in the change of basis in general, you may not get diagonal here. So in this particular case, you're getting diagonal. So this S is a rank 3 matrix, it's invertible, right, because these are independent eigenvectors, the columns are independent, so it's invertible. Anyway, the diagonal has non-zero values, it's lower triangular, so you can quickly see what it is. So you can write with this that, this is AS equals SD. Now you use your matrix algebra, AS equals SD, so A can be written as SD S inverse multiplied on the right, and D can be written as S inverse AS with S inverse getting multiplied on the left. Okay, so this is the basic diagonalization process that we see. I'm showing it to you with one explicit example of how when there's an eigenvector basis, you get a diagonal matrix representation, and how that actually corresponds to this similarity transform, and how you can write it as a matrix multiplication identity. Okay, so now we're going to repeat this very quickly for the other examples. I won't show the gory detail, but just the final answer and how this SDS inverse sort of thing comes about, just to show you the various flavors of these kind of things. Okay, so here is another lower triangular matrix where you have diagonalizable situation. Here are the 3 eigenvectors, 1, 1, 3 are the eigenvalues. So immediately now, going to all of that, the matrix of T in the basis V1, V2, V3 is 1, 1, 3 with the 1, 1, 3 appearing on the diagonal, right? So that's very easy to see. If you have to do a similarity transformation, you can do AS equals SD, and then S is just the eigenvectors in the columns here. Okay, so this way of writing it is also a good way to remember. A lot of people get confused. Should I put the eigenvectors here? Is it SA S inverse or S inverse AS, or how do you do this? I find this useful fact to remember, conceptual way to remember that identity. So you multiply with A, you multiply eigenvectors column at a time. You will get the eigenvectors multiplied by the eigenvalue. Now you can push those eigenvalues to a diagonal matrix on the right. So you get AS equals SD, where S is the columns of eigenvectors. Okay, so it's a good conceptual way to remember this formula. Okay, so again the same thing comes about after this. Okay, so here is another repetition. I'm just going through the same repetition again. Now you don't have the triangular matrix, but then again you get the 0, 1, 2 on the diagonal in the basis V1, V2, V3, and it gives you the corresponding similarity transformation as before. Okay, finally let's look at this example also, where we had repeated eigenvalues for a non-triangular matrix. Again the 1, 1, 4 will come on the diagonal. The constant story of the eigenvalues coming on the diagonal when you go to the eigenvector basis is very, very important and easy to see. Okay, so again you get the same thing. Okay, so a lot of people quite often, if you run a MATLAB program to compute this eigenvalue, the eigen function as I showed you, the ordering of V1, V2, V3 may not be the same. So you will see quite often what you calculate by hand, the ordering may be different. Secondly, the scaling of V1, V2, V3 may not be the same. Okay, so here we see that the V1, V2, V3 are some values. So usually computing programs like to scale the eigenvectors so that they have modulus 1 and all of that. So they do such things. So they may not have the right scale. So be aware of that. The ordering and the scale matter. So sometimes when you diagonalize, you can get 4, 1, 1. What does it mean to get 4, 1, 1? So the basis instead of being V1, V2, V3 would have been V3, V1, V2. Okay, then you get 4, 1, 1 on the diagonal. So all these kind of permutations are possible. So watch out for that if you're using computer programs. Okay. So let's go back to our unusual example. So the unusual example here was this a power k being repeating a squared. But here again you have 3 distinct eigenvalues, and those are going to show up on the diagonal. And you can see, right, in this place, with this a, it might have been not so easy to see that a squared will be something, and then a cubed, a squared will be, you get a and then you get a squared, and then a power 3 is going to be the same as a power 4 is going to be the same as a squared, so on, right? So it may not have been easy to see, but then once you go to the diagonal matrix representation, it's trivial, right? You can see that you will have a, this is your a, so sort of not a, when a in the other basis, right? So a, and then when you square this, you're going to get 0, 1, 1. It's got just 0, 1 and minus 1 on the diagonal, right? So this minus 1 squared is going to become 1. And then when you raise it to the power 3, a power 3, you're going to get 0, 1, minus 1 again. Okay, because this is diagonal, now the diagonal values are getting raised to the same power, right? So you see how odd and even powers repeat here. It's very, very easy to see in the diagonal form. Okay, so why did this matrix end up having this kind of a picture? It's because it was diagonalizable and its eigenvalues were 0, 1 and minus 1. Okay, so because of that, this property ended up being true. Okay, so So yeah, I hope you see that, because 0, 1 and -1 are the only numbers which repeat in power, right? And if you have a matrix whose eigenvalues are only 0, 1 and -1 and it is diagonalizable, then its powers will also repeat, just like 0, 1 and -1 repeat. So it starts behaving like 0, 1, -1 in some sense. So this is how you sort of bring this unusual property in for these non-trivial matrices. Okay, so again you can check that this similarity transform is also true here. Okay, so I hope I gave you a flavor of all these kind of examples of how diagonalization can be done, and understanding the similarity transform and understanding the matrix of a linear transform with respect to the eigenvector basis. So when you do the change of basis, what happens to that representation, and all of that is very, very interesting. I hope these examples clarified some of those ideas for you. Thank you very much.